Hello there, young scientists. Have you ever wondered how you manage to sprint in PE class, your phone lights up with just a tap, or how the sun keeps our planet warm and alive? The answer to all of that is energy. In physics, energy is not just an idea or a feeling, it is precisely defined as the capacity to do work. Everything that happens in the universe, from a tiny mosquito flapping its wings to rockets blasting into space, happens because energy is being transferred or transformed. When work is done on an object, energy moves from one body to another. The object that performs work loses energy, and the object that receives the work gains it. We measure energy in joules, symbol J. And for larger quantities, we use the kilojoule, symbol kJ, where 1 kilojoule equals 1000 joules. So, the food you eat, the fuel that burns, and even the sunlight that warms your skin, all of them are forms of energy waiting to do work. Pretty cool, right? Now, let's explore how energy appears in different forms. It's the ultimate master of disguise. Energy can exist as mechanical, heat, chemical, electrical, light, or even nuclear energy. These are just different faces of the same physical quantity. For example, when sunlight helps plants grow, solar energy gets stored as chemical energy in food. When you eat that food, your body turns it into mechanical energy to move your muscles. Almost all the energy we use traces back to the sun, the greatest power plant in the solar system. It powers winds, ocean tides, and even the growth of fossil fuels deep underground. However, there are non-solar sources too, like geothermal energy from Earth's hot core and nuclear energy from atoms. In short, energy is everywhere, transforming, transferring, and keeping life and motion alive across the universe. Alright, let's move, literally, into kinetic energy, the energy of motion. Whenever an object moves, it has kinetic energy. The faster it moves or the heavier it is, the more kinetic energy it carries. So a fast-moving cricket ball, a flying airplane, or even a gentle breeze all have kinetic energy in action. The mathematical expression for kinetic energy is E sub k equals 1 by 2 multiplied by m multiplied by v squared. Where E sub k is kinetic energy, m is mass in kilograms, and v is velocity in meters per second. Now here's something fun. Notice the velocity is squared. That means if you double the speed, the kinetic energy becomes 4 times greater. So a car traveling at 60 kilometers per hour has 4 times more energy than the same car at 30 kilometers per hour. That's why speed can be dangerous. Physics never lies. Every rolling stone, flowing river, or flying bullet carries kinetic energy, the power of motion itself. Now, what if an object isn't moving but still stores energy, waiting to do work? That's potential energy. Potential energy exists when an object's position or shape gives it the ability to perform work later. When you stretch a rubber band or lift a book, you're storing energy in it. The gravitational potential energy of an object raised to a height is given by the formula E sub p equals m multiplied by g multiplied by h. Here, E sub p is potential energy in joules, m is mass in kilograms, g is acceleration due to gravity, that's 9.8 meters per second squared, and h is height in meters. Let's say you left a 1 kilogram book to a height of 1 meter. The potential energy gained is approximately 9.8 joules. Drop it, and that potential energy instantly transforms into kinetic energy as it falls. So, whether it's a stretched bow ready to shoot an arrow or a waterfall high above the rocks, both hold stored energy, waiting to burst into motion. Time to do some real physics magic. Let's derive that famous formula for kinetic energy. Imagine an object of mass m starting from rest, which means initial velocity u equals 0. You apply a force, F, that moves it through a displacement s. According to the work formula, W equals F multiplied by S. Now, from Newton's second law, F equals m multiplied by A, where A is acceleration. And from equations of motion, v squared minus u squared equals to multiplied by a multiplied by s. Let's substitute. Work done, W equals m multiplied by a multiplied by s. Replace a multiplied by s with v squared minus u squared divided by 2. That gives W equals 1 by 2 multiplied by m multiplied by v squared minus u squared. Since it started from rest, u equals 0, so the equation simplifies to W equals 1 by 2 multiplied by m multiplied by v squared. That's it, the work done equals the kinetic energy gained. So, E sub k equals 1 by 2 multiplied by m multiplied by v squared. This shows that every bit of work done on an object turns into energy of motion, and that's the heart of the work energy principle. Let's wrap up our energetic journey with one of the most powerful ideas in all of physics, the law of conservation of energy. Energy can neither be created nor destroyed, it can only change form. The total amount of energy in a closed system remains constant forever. For example, imagine a pendulum swinging. When it's at the top, it has potential energy. As it swings downward, that energy turns into kinetic energy. At the lowest point, all potential energy is converted into motion. As it rises again, kinetic turns back into potential, and the total always stays the same. We express this as E sub p plus E sub k equals constant, where E sub p is potential energy and E sub k is kinetic energy. This law explains everything from waterfalls turning turbines to rockets flying into space to even how your body converts food into energy. So, in the grand story of the universe, energy is never lost, it only changes costume. From heat to light, from motion to rest, it flows endlessly, keeping everything alive and in motion. I hope this session gave you a spark of excitement about how energy powers everything around you. Until next time, keep asking, keep observing, and remember, in physics, energy is eternal, it only transforms.